Okay, we're going to have one more video here talking about solving triangles, and this is going to be dealing with the angle-angle case. Of course, as you know, we have a little bit of a problem in the angle-angle case because no matter what we do, it's easy to find the other angle. We just use the angle sum theorem. But there's no way to know what the sides are because any of these triangles that you see here are all have the same angles. So there's actually infinitely many different triangles we can come up with. But on the other hand, that doesn't just mean that anything would work. All these triangles are similar, as we've seen earlier. So let's see what we can do in terms of doing some solving for this. So the best thing we can do here is to basically do something like this. So it's impossible to come up with a specific triangle. Well, not impossible to come up with a specific triangle. It's impossible to only get one triangle for this because there are many, many, many different ones. So of course we start with the easy thing to do, which is use the angle sum theorem to calculate the third side. So if we're given two triangles with sides with angles given, say A and B. Now of course if those angles are more than 180 degrees or more than pi radians when you add them together or are equal to that, there's no such triangle. But if they're smaller, then you could always make a third angle by subtracting from 180 degrees or from pi radians. So C equals 180 degrees minus A minus B. That finds the third angle. Now, we can use the law of sines to compute the lengths of one triangle from this family where C is 1. So we think about an example here. Here's an example, this little one down here, where C is 1. So let's solve this particular black triangle down here in the bottom left, the one where I have labeled as ABC, and then I have A1, B1, C1 for the green one, and A2, B2, C2 for the purple one. So we're going to use this little triangle down here, which the numbers are down here in it. Okay, so let's solve that particular triangle, and then we're going to go from there. So we know A over sine of A, this should be capital, is C over sine of C. So multiply both sides by sine of A, and then plug this in. Little c is 1, so we get this side A is sine of capital A over sine of capital C, and that's supposed to be 0.74. And let's just check that out with the calculator here. And I'm not going to do every one of these on the calculator. I'll let you check them yourself. So you can pause the video at any point and you want to check these out. So let's see, we're in degree mode, which is fine for the moment. And so we're going to do sine of angle A, which was 40 degrees, and divide that by sine of angle C, which is 60 degrees. And this should give us side A, which is that. Let me store that as A. And let's do side B. Okay, in a similar way, it's sine of B over sine of C. So I can just pull up my previous answer back here, a couple back, and change the one on the top to angle B, which is 80, and C is 1. And so we have this set up here. There's B, so let me store that as B. So now we've solved for A and B, 0.7422271199 approximately, or approximately 0.74 for A, and about 1.14 or about 1.137158043 for B when C is 1. So we have three sides. So now we have a specific triangle, and then we can go ahead and find its area. 1/2, 0.5, times A times B times the sine of angle C, 60, and that should give us the area. Okay, let me store that as K. And so we have the area. Now that's for this one specific little triangle that you see over here on the left here. Okay. Now, any triangle, all these other triangles like this one here, is just a size transformation of that other of the other triangle. Okay. So we just need to figure out what that size transformation is. We can apply it to this little triangle and get the bigger one. So let's take our factor, well, C, because C is this side 1. So we'll take our new C, and that'll be side C. And then B is going to be C times whatever we found for B for that special triangle down here where C was 1. And then A is, well, whatever we found for A before times this C. But the angles are the same. So this is a similar triangle here. And our proportion, all the sides are proportional. C becomes the proportionality factor. And so we know we have that. Now, when we do this, you have to be a little careful because remember that on a triangle, let's say you have B1 is C times the original B. Well, let's say B, let's do this. And B1 was the one we came up with in our solving. And C over here is 1, C1 is 1, and A1 is whatever we come up with. Okay, so B is B1 times is C, whatever C is here. This C times B1 is this B. Well, these are supposed to be similar, so they should have the same kind of a shape. Let me get it at least a little closer, so it seems reasonable. Okay, now whatever this, we need to find the height here. Okay, and whatever that height is, we're going to get C times that height here for the height over here. So, what's the area over here? The area over here is, we'll call it B1 times H1 times 1/2. We'll call that area 1. This is area 2. Well, this is, we could call this H2, we could call this B2. It's 1/2 B2 times H2. But B2 is C times B1, and H is C times H1. So if you notice, you can factor out a C square, and you're left with 1/2 B1 times H1. So in fact, that is A1 times C square. So notice, whenever we have a proportionality factor, and we have similar triangles, what happens? Well, it doesn't do anything at all to the angles. The angles stay exactly the same size. What does it do to lengths? Lengths are all multiplied by this proportionality factor, which we're calling C in this case. But what happens to the area? The area gets multiplied by C squared. So, the new area is C squared times whatever we calculated here for this one area. So, for example, let's take the green one, and if I set it in the right place, right now, let's see, I've got it, let's see if I can make the length twice as big. Yeah, I'm close. 1.99. So about twice as big. And so you see that the length here is roughly twice as big for all the lengths. So whatever this C was here was 1. This is actually about 2 here. Okay? And so whatever's A here, about 0.74, the A1 here is about twice as big. So, you know, about 1.4, 1.5, something like that. Okay, and so forth. So all the lengths are twice as big, but the area is 4 times as big. So the area here is 0.37. 4 times that is what we get up here. Okay, and so you can kind of see that here. So what do we do in the angle case? The best we can do is to sort of get a basic example, and then use that basic example then to generate all the sets of values that you could have. There are infinitely many such triangles, but we actually solved all infinitely many here because they are all proportional sides, and so we were able to do that. So what did I do again? Let's review. I just picked one of the sides to be 1. It actually can be any one. I picked C. So pick C to be 1. Then I can solve for A and B using law of sines, and use then that information to solve for the area. Once I have all 3 sides in the area of that triangle, of course the angles, I guess I should back up. First thing, of course, is just find the other angle. That's pretty straightforward. Law of the angle sum theorem. Then I let one side be 1, say C is 1. Use the law of sines to solve for the other 2 sides, use the information above to solve for the area of this particular triangle. Then in general, what happens is the general triangle, the angles are the same as that specific example that you worked out. C is whatever side you let be 1, that'll be your proportionality constant, so we'll call that one C. Then A is C times whatever we found for that special triangle. B is C times whatever we found for that special triangle. And then the area is C squared times whatever the area was for that special one. And so this is the setup in general, and you can let C be any positive number, and this turns out to be a triangle that fits the angle-angle condition that we began with. So that's the best we can do. Okay, before I finish, let me also finish up this by showing you another, if I can find it real fast, another file that I have that I will have posted. I can get my hands on it quickly enough here. So there's some some notes on solving triangles, and it looks something like this. And this goes over the basic, reminding you the basic setups for right triangles and then for all triangles. Okay, and then right here, it goes back through the derivation of the law of sines and cosines, but here is the solving triangles part. Actually, I'll probably just make a file that just has this part right here, and this one reviews solving right triangles, which you've seen before. But if you go down below, down here, we can see solving all triangles here. Where am I? Okay, again, right triangles. Let's go past the right triangle part. So this has all the possibilities. So solving general triangles is down here. Okay, and I go through every case. Side angle, side case. It's static notes, not the dynamic stuff that you see in Sketchpad, but it does some of the same things here. But it does give you a static example you can print out. Here's an example. The example was created in Sketchpad, and so the sides should be fairly close. Oh, lost my place again. So here's an example. It goes through all the different cases. Side angle side is here. And it gives you an example. But then also after the example, and of course it shows you all the work. And then it gives you an application, a real-world application that goes exactly with that particular example. And the answer to that real-world example. Okay? And it will have some practice problems underneath each one as well. And of course you can check your practice problems by going to the Sketchpad sketch and you can use the model that's right above. This talks you through it without going through the details. It does talk about what you can do in these other cases where there are where you know the area and some other information. Okay, and so here if you have a K and two angles, you can proceed in the angle case, but then you can use knowing what K is to solve for the special proportionality constant, and that will narrow it down to this particular one. There's area, side, and angle where the angle and side are adjacent. There's one triangle is possible there, and so you use this formula here to solve for the missing side, and then you're like in the side angle side case. If you have a side and opposite side and an angle opposite and the area, okay, then you can use this formula here in the law of cosines, and but it gets a little messy. Okay, so when you work this out, I had to use some special software to solve here, and you get this messy formula here, and you can use that. But that's solving this fourth degree equation, so that's a bit of a mess for that one. So I will not be asking, for example, especially case 9 for sure, will definitely not be asked on an exam, that's for sure. So this kind of goes through the different possibilities. Okay, so I will post that particular file as well for more help.